Just checking it out. Was there last semester, part of the semester? Yeah. That's, I didn't. Oh, fine. Okay, great.
Good morning. I'm Rakesh. I'm a postdoc at Hebrew University. I will be speaking on multiplayer parallel repetition for expanding games. And this is joint work with Elite Advisement, Prahlad at TFR, and Henry from Berkeley. Okay, so let me start off with the basic setting, although most of you are familiar with it, but I'll go through it in. Okay, so we have kind of two non-communicating provers, and they want to win in a game against a verifier V. Okay, so the verifier draws questions from a globally known distribution, and it consists of a pair of questions, one of which goes to P1 and the other goes to P2. Okay, and now they are supposed to respond back with answers based on just the questions that they have received, because they can't see the other prover's questions. And they win if a verifier predicate evaluates to 1 on the answers that they give. Okay. So of course they have to come up with some sort of strategy to do this. And the value of the game is defined as kind of the maximum probability that they win. That is, they need to use good strategies too. Okay, and there's nothing sacrosanct about k equal to 2. One could generalize this to many more players, and we have exactly the same setting. Again, the value of the game is the probability of winning. Okay, so as I described, it used only deterministic strategies, but you can say that what about randomized strategies? Turns out it doesn't help much. You could just give a fixing of the random bits R, and you'll get a deterministic strategy with at least the same value. But it's a useful tool in analysis, and we'll use it. Okay, so the construct that we want to analyze is the n-fold parallel repetition. Okay, so what happens in this? The verifier draws not one tuple of questions, but n tuples. So all of them are drawn IID from the same distribution D, and the respective parts are sent to the provers. Okay, so for instance, P1 receives x1 to xn, P2 receives y1 to yn, and so on. Okay. And now they have to respond back with answers on every coordinate. So the answer is now a vector, it has a1 to an. And the verifier now evaluates the predicate on every single coordinate, and the players win if they win every single coordinate. So of course this is much harder than just doing one instance of it at a time. So this n-fold repetition is also a k-player game, of course, just that the alphabet sizes are blown up, the question set sizes are blown up, and it should be clear that if the original value is 1, then the n-fold repetition has got value 1. Okay. And one could be tempted to claim that the value does go down as 1 minus epsilon to the n if the original value was 1 minus epsilon. However, this turns out to not be the case, and there are simple two-prover games as suggested by Feige and Fort now, such that the value of the two repeated game is equal to the value of the original game. Okay. And it turned out to be a non-trivial question to ask whether there is any sort of decay in the value of the game under repetition. Okay, so we do understand the case pretty well for two players. So for instance, Verbitsky first showed that the value does go to 0 as the number of repetitions goes to infinity. And Raz was the first one to take the previous exercise seriously and showed an exponential decay. And there were subsequent improvements. So if you notice, the game value does go down, although it's not 1 minus epsilon to the n, it's something that is exponential in n. And there were subsequent improvements and simplifications. One thing I wanted to note is that there's a dependence on the game parameters of some sort. For instance, here, the denominator s here in the exponent is the answer length of the players. Okay, So that was the case k equal to 2. We have exponential decay, and that's very good. But what about more than 2 players? Turns out very less is known. Verbitsky's proof still holds and gives an inverse Ackermann decay for games. However, all other proofs do break down. And this is because they involve a certain correlated sampling step among players that doesn't generalize. Okay. And this technical roadblock is similar to one seen in proving direct product results in various other models such as communication complexity. Okay. And the only thing we know is that there are better decay bounds for certain specific classes of games currently. Okay. For instance, if the game was free, that is, the questions to the players were just product distribution, then there is an exponential decay bound. And if the game was anchored, in some sense, that is, the verifier kind of corrupts certain coordinates to confuse the provers, then too we do know an exponential decay bound. So besides these two, we don't have any other results currently known. And one might pause to ask as to why are we considering parallel repetition at all for the case of k greater than 2. Well, first, parallel repetition has got certain, it's a direct tool used for showing hardness amplification for CSPs problems in general. And also these proof techniques could help us make progress on similar questions like direct product theorems in communication complexity. Also, besides, the main reason for me is it's pretty maddening that we do not know better than inverse Ackermann decay bounds for even very simple 3-player games that was mentioned. So this is the GHZ game. The GHZ stands for the authors who introduced it. Okay, so in this, it's a very simple 3-player game, and the verifier basically draws 3 random bits. The bits are just the questions, conditioned on the fact that x, XOR y, XOR z is equal to 1. And he sends 1 bit to each player, x to p1, y to p2, z to p3. They have to answer back with bits a, b, c, and the predicate that is evaluated is x and y and z equal to a XOR b XOR c. So for this game, we do not know any kind of decay bound, even though it's so simple to describe. Okay, so let me just state in this context our result now. So what we show is that all games which are expanding in a certain sense do obey an exponential decay bound, even for k greater than 2 players. And this recovers the exponential decay theorems for free and anchored games. And also, of course, it extends to a larger class of games. So here's the statement of the main result. So if G is a k-player game and the value is less than 1 minus epsilon, if a certain graph connected with the game, which I call the k minus 1 connection graph, is a lambda expander, then the value does go down exponentially.
I have a question. So in prior results, there was dependence on k in the denominator.
Yes.
Is it implicit in the lambda here?
Yes, it is implicit in the lambda. When we apply it to the classes of free and anchored games, the lambda will be inversely dependent upon the number of players. It will just turn out naturally. So let me just describe to you next what is this k minus 1 connection. So for sake of clarity, just take k equal to 3 because this is kind of the hardest case to move on from 2, and it will extend to larger k pretty easily. Okay. So the vertex set of the graph is just the set of all possible question tuples. Okay. The graph is weighted, and there's a weighted edge between 2 question tuples q and q prime if the Hamming distance between them is at most 1. So it has self loops and edges to other vertices at distance 1 from it. Because it's weighted, we'll define the degree of a vertex as just the sum of the weights of all its out neighbors. So I won't describe the weights because it's not really important. Suffice to say that we set the weights in a very natural way so that the degree of a vertex turns out to be the probability of that question being asked in the game. And in this context, there might be question tuples that never get asked from x cross y cross z, and we just forget about them when we talk about properties such as connectivity, expansion, etc. So just keep this in mind. Okay, so here's a diagrammatic representation to consolidate what we said. So notice here x, y, z, all the vertices have self loops, and x, y, z is connected to x, y prime z, but is not connected to x prime, y prime, z prime. And if a vertex has got 0 weight, we just ignore it totally. So yeah, I hope this definition is clear. It should look something like the k-dimensional hypercube, because you're connecting points at distance 1, but just over a larger alphabet. Just the edge weight, we don't need that. The other thing that I want to say is our notion, just go over what is an expander. So the way we look at it is, if H is a lambda expander, and if we associate a vector G with every vertex in this, it could be an arbitrary vector, such that basically the squared distance between every edge in the graph on average is bounded by delta, then all the vectors are close to their mean by a factor delta over lambda. So this is nothing but the definition of the second smallest eigenvalue of the Laplacian of this graph. So again, if the edges are close under this vector assignment, then all the vectors are close to their mean. Okay, so how do we use the expansion of the k-connection graph? Basically, we use it to bypass this roadblock that I talked about. And using this, let me just give you a sketch of the proof of the main result. Okay, so here's the result again. And what is the strategy we use? Well, it's a proof by contradiction, just like the two-player case. That is, if the value of G fold n is much larger than this, then we are going to get out a strategy for G, the single base game, that is impossibly good, that it is win with probability greater than 1 minus epsilon. And that should not be possible. And the idea is basically that to use shared randomness to sample the remaining coordinates of question. So this is very similar to previous known proofs of the two-player case. So again, in some more detail, let W be the event that they win all the coordinates. Of course, it's the AND of all the single coordinate wins. Well, if you just expand this out by chain rule, one of these terms have to be large if the entire term is large. Okay. So what one can show is that there exists a coordinate I and a subset S such that one of these terms is larger than 1 minus epsilon by 8. And so this suggests a very natural strategy for G. What do you do if the players receives x, y, z? They are going to sample the remaining coordinates, which I call as R by a random variable R, conditioned on this event, Ws, and the fact that they receive small x, small y, small z in the ith coordinate. So what this means is that if they now answer G according to coordinate I, they win with probability greater than 1 minus epsilon by 8, which is a contradiction and should not happen. But of course, there's a problem in this. The problem is that no single player knows all parts of this conditioning event. So for instance, player 1 does not know y and z. So he won't be able to condition on this event and draw this random variable. And this is the problem that one has to bypass. What happens in the two-player case? In the two-player case, again, the goal is to embed game in this I, given that you win in Ws, and you want to sample the remaining coordinates conditioned on the fact that you have x, y, and Ws. So the main lemma, a key lemma that was used by Raz and Hollenstein was basically that, well, you just look at the distributions that the players do have in hand, and that is R given x and Ws, and R given just y and Ws. This is with P1 and this is with P2. And they are actually kind of delta close in L1 distance to this target distribution that we want to sample. So this is great because now since they know the distribution, they can sample in a correlated fashion, okay, and approximately win the game. So they incur some amount of delta error in doing this, but they still end up winning G with probability much greater than 1 minus epsilon. So this was the general proof idea. Of course, I'm hand waving a lot and I'm skipping out details here. But let's see, why doesn't this extend for the k greater than 2 case? Okay. So the situation is the same. We now want to sample the remaining questions according to x, y, z, and Ws. So it's conditioned on x, y, z, and Ws. But if you extend the previous lemma directly, all one gets is the following, that R, X, Y, Z and W, R conditioned on X, Y, Z and Ws is close to those conditioned on two variables at a time. And now, although this does reduce the dependence on the unknown question, it's not good enough for 3 or more players because none of the players know of any of these distributions because they have only access to either X or Y or Z. So now how do we get around this? Well, we use the expansion of the graph, of the k-1 connection graph to get around this. So here's a way to rephrase the closeness. Well, what we know from the previous extension of the Hollenstein-Rawls lemma is that R condition on X, Y, Z is close to R condition on just X, Y. But then using a simple triangle inequality will give that R condition on X, Y, Z is close to R condition on X, Y, Z prime for any Z and Z prime. Now notice that these two are adjacent vertices in the k-1 connection graph because they differ just in one coordinate, which is Z. So what does that mean? So now we can exploit this because what we do is with every node in the k-1 connection graph, you associate the vector, which is the distribution vector of R, conditioned on this. Okay, so for instance, X, Y, Z has the distribution vector corresponding to R given X, Y, Z and Ws. So now we have these sets of vectors at every point in the graph. The graph is an expander. Notice that this closeness basically says that adjacent vectors are 2 delta close, and hence expansion will give us that there is a global distribution that all of them are close to, off by a factor of lambda. Of course, this was L1 norm. In the expander sense, we need to work in L2 norm, so we lose a square root factor, but that's about it. So basically what this states as of now is that we have one global distribution which is close with delta over lambda close to all of these distributions. So instead of, the goal was to sample from one of these, but now they can just sample from this global distribution and not lose much. And so they will win the game G with probability 1 minus epsilon over 8 plus the error loss, which looks like square root delta over lambda. And since the delta setting was small enough, this still is greater than 1 minus epsilon, giving us the desired contradiction. So this is just the basic idea of the proof. There are some more details that need to be taken care of, but not very much more. Okay, so what do we get from this? Well, turns out that let us see how we recover the previous cases. That is, for instance, for free games, turns out that the k-1 connection graph is just a high-dimensional hypercube, and the eigenvalues are well known for this. And if you just plug in the eigenvalue bound into a main result, we do get an exponential decay bound for free games. For anchored games, similarly, the k-1 connection graph is a layered graph, and it has low congestion. So this again gives us a lower bound on the eigenvalue. And finally, the most general class of games that we can handle somewhat is the class of connected games. Okay. That is, if the k-1 connection graph is connected, then lambda, which is the second eigenvalue, is greater than rho min, which is the minimum weight on any edge. Okay. So for instance, if the game had full support, then they do have a connected k-1 connection graph. And for such games, there was a bound known, exponential decay bound known for the non-signaling value of the game, but it was not known for the classical value. So yeah, this recovers most of known results. And finally, in conclusion, what we did was we introduced the notion of connectedness to yield exponential decay for a large class of games, and this recovers previous known results. But for instance, we still cannot handle the GHZ game that I mentioned before, because if you look at the k-1 connection graph of the GHZ game, it has only isolated vertices. And so there are very strong correlations among the question pairs, and somehow our approach cannot handle that. So how do we kind of prove exponential decay bound, say just for the GHZ game is itself interesting. And finally, notice that for our connected game bound, the eigenvalue depended upon the minimum probability of minimum weight of any edge in the k-1 connection graph, and this depends on the game size description. And that is not ideal. We would want something much better than that. So can the dependence on the game size be dropped from? That's the question.
right now this kind of dichotomy between games where we only know inverse Ackermann and games where we know exponential. Right? Is there
Kind of.
Are there games in the middle? Do we know polynomial decay bounds for any interesting class of games? Or
For k greater than 2, I don't think so. No, not as far as I know. So anything that is, yeah, it's this, as you said, it's a dichotomy. For 2 provers, we know a lot, we know exponential decay. For more than 2 provers, there's hardly anything known.
That's kind of a naive question, but like there are a lot of parameters. What exactly are the ones that matter for the applications? Like the dependence on epsilon, for example, is crucial, or is it more like the dependence on s, etc.?
Okay, so it's as of now for most of the applications that are there can be handled with just like 2 prover cases, 2 prover game result. But the main thing for that we'll need for further applications of this is the dependence on n. That's all.
Do you have any idea of what if any combinatorial objects might be relevant for the GHZ game, or? I mean, it
Not
seems like
really. It's just we don't know yet. Yeah. We've not thought much about it, but I'm not sure.
And also, I guess that was the answer. So for the 2-player case, the dependence on the alphabet, the size of the alphabet answers, is it known that it's necessary?
Yes,
or?
that is necessary.
Okay, but then for the last question there about the game size, that's a different additional
Yes.
dependence that it's not sure whether it's
Yes, so the game size is basically the size of the game description, which might include things like the number, the size of the question set, or the minimum probability of any question appearing. So, yeah, it's, for 2 prover games that is not necessary, and it's not clear whether that is even required for k prover games.
All right, so let's thank Rakesh again.